combination of condensers. Condensers might be connected just like resistances or the springs. Condensers also could be connected in series, parallel, or even mixed. First of all, we'll consider the series combination in which the condensers are connected one by one in such a manner that one plate of the first plate of the condenser is connected to the second plate of the previous one. And if the charge is obtained by this condenser plus Q, this is minus Q. Induction. Plus charge that will be produced here will automatically be transferred to first plate of the second condenser, and similarly it will have minus charge. So you could say that the charge obtained from the source was simply Q. All other charges were either by induced or by the transfer, but from the source it was simply Q. So total charge here will be Q. But the potential difference shall be divided. Suppose it is total V, then in that case V is going to be V1 plus V2. Potential difference will be in the ratio, you see, it's Q by C1 and then it is Q upon C2. That way you could see potential difference is divided in the inverse ratio of their capacity. Similarly, if you want to add the potential energy, it's going to be the sum of the two. And if you use the relation half Q square upon C, why this? Why this formula in terms of charge? Because all the condensers are having the same charge. We'll prefer this relation, and in this case U1 upon U2, this is equal to C2 upon C1. So you could say that potential difference and potential energy both are divided in the ratio inverse that of the capacity. Now, how to find out the total capacity here? Once you say V1 plus V2 is V, then obviously it's a Q upon C1, Q upon C2. It's going to be Q upon C. I told you the total charge will also be Q. Charge individually on each condenser will also be Q. All gets cancelled. It is 1 upon C1 plus 1 upon C2. In this case, the equivalent that you are going to have shall be less than even the smallest value in the combination that we prefer. If you are having n equal charges and all are connected in series, obviously you are going to get the result C upon n. You are having only two condensers. In that case, the capacity will be this one. You are having three, it's going to be C1, C2, C3, C1, C2 plus C2, C3 plus C3, so on, C3, C1, so on. So, it is the pattern you could follow for any number of condensers. Let's talk about parallel combination now. In parallel combination, all the condensers will have one plate connected together, other plate connected together. This is the style in which we shall connect the network in parallel. If the potential difference on the source is V, it's going to be on all the condensers connected in parallel. Obviously, V is not divided, only the charges shall be divided here. Say it is Q1 and Q2. Then in that case, Q will be equal to the sum of the two, Q1 plus Q2. If there are three, you could continue. And by using CV, this relation C1V plus C2V, you get simplest result for combining the capacities of the condensers. It is equivalent capacity. Obviously, here the equivalent capacity will be greater than the biggest value in the group that we used here. If you want to check the ratio of charges again, this is going to be the direct ratio. If you want to check the ratio of electropotential energy, better you prefer this relation, and in this you see V is going to be common, then in that case U1 upon U2, it will be C1 upon C2 simply. And then let's compare both the combination. If you are having n condenser, once you connect in series, then you connect in parallel, and you try to find out the difference. In the two cases, you'll have the result, the difference of the two. At the same time, if you get the ratio, Cp is going to be Np, Cs is going to be C upon N, you could multiply and take the ratio also. There was one very important principle that's used in complex electrical circuits in later stages, that's Wheatstone bridge. Although it's more common for resistances, but it is equally important for condensers as well. Suppose you are going to have 4 condensers. You see, when you say Wheatstone bridge, it simply means that along the 4 sides of a quadrilateral, you are going to have 4 condensers. There is no any condition for Wheatstone bridge. Condition is simply that it should be a quadrilateral and there should be 4 condensers along each side. Suppose you connect along one diagonal, one cell. It might be some key also over here, and between the other diagonal you can use anything of your choice. See, A, B, say this is A, B, D, and F with the figure VD and VF. You see, it's fine D. This whole set will be known as a balanced Wheatstone bridge only when one special condition is followed over there. C1 by C2, that's equal to C3 upon C4. In this condition, obviously you have one particular result, that these two, that is D and F, these 2 points will have no potential difference. VD is going to be VF, potential of both the points, both the ends of a diagonal. It's going to be at the same potential, no potential difference. And in electricity, entire charismatic affair is that of current flow. Current will flow only when there is potential difference. Once you decide there's no potential difference, it simply means that anything you connect between the two, it might be resistance, it might be condenser, it might be even the coil also, in all the cases that will be ineffective. So, any condenser if you use between B and D, when the bridge is balanced, it's not going to be effective. One more condition, if C1 upon C2 is greater than C3 upon C4, in that case you could directly say that potential of D is going to be greater than potential of F. If this ratio C1 upon C2 is greater than C3 upon C4, then potential of D is going to be greater. This you have to remember. And finally, you have to remember one result which you could derive also as and when required. Suppose along the 12 sides of a cube, if we use the condenser all of equal capacity C, then we could find the equivalent capacity between the two ends. Now, it will depend where the two ends have been taken. If the two ends are that of a body diagonal, it's going to be 6 C upon 5. And if the two ends are that of a face diagonal, it is going to be 4 C by 3. And if you choose the two ends that of a single side, single edge of the cube, it's going to be 12 C upon 7.